Quantum numbers give the address for an electron. Electron configurations give a broader picture that includes all of the electrons in an atom. They list all of the subshells in an atom in order of increasing energy, and they tell how many electrons are in each subshell. This would be like listing all of the streets in a city and then telling how many people live on each street. It does not get down to the level of the individual, but gives a lot of information at once. Let's start with the simplest atom, hydrogen. The ground state electron configuration for a hydrogen atom is 1s1. When we say ground state, we are referring to having the electrons in the lowest energy configuration possible. This is how they are normally found. The 1 on the left of 1s1 refers to the principal quantum number n, which in this case is equal to 1. The s tells us the shape of the orbital and has a corresponding L value. In this case, it is spherical and has an L value of 0. The superscript of 1 tells us that there is only one electron within the 1s subshell in hydrogen. Electron configurations are written in order of increasing energy. For now, you can follow this diagram from bottom to top. 1s is the lowest in energy, followed by 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p, etc. After writing out the orbitals in order of increasing energy, you will need to fill in some superscripts. The total of the superscripts should add up to the total electrons in the atom, which for a neutral atom will be the same as its element number. You will start with the lowest energy orbitals and fill them to their maximum capacity until the total reaches the total number of electrons in the atom. The maximum capacity depends on the orbital type. S orbitals have one orientation, so there is one s orbital within an s subshell. Each orbital can hold a maximum of 2 electrons, so the maximum an s subshell can hold is 2 electrons. You would write a superscript of 2 on all of the lower energy s orbitals in your electron configuration. P orbitals have 3 orientations, x, y, and z, so they have 3 orbitals within their subshell. Since each orbital holds up to 2 electrons, p subshells can hold up to 6 electrons. You would write a superscript of 6 on all the lower energy p subshells in your electron configuration. These subshells contain 5 orbitals, so they can hold up to 10 electrons. F subshells have 7 orbitals, so they can hold a maximum of 14 electrons. The last subshell in your electron configuration may not be filled to its maximum capacity. Remember, you are limited to the total number of electrons in the atom. The last subshell will hold as many electrons as needed to reach that total and will be equal to or less than the maximum for that subshell. Let's look at an example. We want to write the electron configuration for cobalt. First, we use the chart from slide 54 to write the orbitals in order of increasing energy. We don't necessarily need to write every single one, but we will write a bunch of them, starting with the lowest energy and working our way up. Second, we fill in the lower energy orbitals to their max. We put superscripts of 2 on all of the s subshells and superscripts of 6 on all the p subshells. If there were d's, we would put a superscript of 10, and if there were f's, we would put a superscript of 14. We keep count as we put each of them in, so we make sure not to put in more than the element number. Once we have filled up to 4s2, we count that our total is 20 electrons filled in so far. Since cobalt is element number 27, we need 27 to be our total. The final subshell we need to fill in is the 3D subshell. We are not going to fill it in with the maximum of 10 though, because that would push us over our 27 electron limit. We only need to fill in 7 electrons to reach our total of 27. Our final electron configuration for cobalt is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. That tells us there are 2 electrons in an s subshell in the first energy level, 2 electrons in an s subshell in the second energy level, 6 electrons in a p subshell in the second energy level, etc. You will need to be able to write electron configurations without referencing slide 54, so you will need a way to figure out the orders of the energies of the subshells. One way is with this arrow diagram. To draw this arrow diagram from memory, put all the S's in a column, the P's in a column, the D's in a column, and the F's in a column. Then number each row from top to bottom. The S's should start with 1, the P's should start with 2, the D's should start with 3, and the F's should start with 4. For example, there is no 1P. Draw diagonal lines from top right towards bottom left. Trace the lines from the base of the arrow to the tip of the arrow, then base of the next arrow through tip of the next arrow, and so on. As you move through the arrows, write out the subshells in order. In my opinion, a better way than using the arrow diagram is using the periodic table. You just need to divide the periodic table into 4 blocks and number the parts of those blocks. The left 2 columns of the periodic table plus helium make up the S block. The S block numbering is the same as the row number on the periodic table. The sort of square on the right side of the periodic table is the P block. The P block starts counting with 2, but also corresponds to the row number on the periodic table. The S's and P's that are in the same row have the same principal quantum number n. The D block is the rectangle in the middle of the periodic table. The D block starts counting with 3 and is always 1 lower than the S and P values in the same row. So for example, after 4S, it steps down to 3D. The F block is the lanthanides and actinides. The F block starts counting with 4 and is always 2 steps lower than the row number. So for example, in the 6th row, it goes 6S, then 5D, then 4F, then back up to 6P as we go from left to right. Once you have the blocks figured out, you just work your way through the periodic table from top to bottom, left to right, the same way you would read a book. As you do, write down the subshells you encounter in the order you encounter them. You can fill in the superscripts, again, keeping in mind their maximum, but you can also count elements within a particular part of a block. This is especially useful for quickly determining the configuration of the outermost subshell of an element. For example, let's say you are finding the electron configuration of nitrogen. Since nitrogen is the 3rd element of the 2p part of the p block, the electron configuration for nitrogen ends in 2p3. Which of the following electron configurations represents silicon? Is it A, 1s2, 2s2, 2p6, 3s3, 3p2? B, 1s2, 2s3, 2p6, 3s2, 3p2? C, 1s2, 2s2, 2p6, 3s2, 3p2? Or D, 1s2, 2s2, 2p6, 3s2, 3p4? The correct answer is C, 1s2, 2s2, 2p6, 3s2, 3p2. You can work your way across and down the periodic table. Hydrogen and helium would be 1s. That's 2 elements, so the superscript would be 2. Lithium and beryllium would be 2s2. Boron through neon would be 2p6. Sodium and magnesium would be 3s2. Silicon is part of the 3p's and is the 2nd element within that section, so the ending part of the configuration should be 3p2. Notice that the total number of electrons is incorrect for answer choices A, B, and D. Also notice that in answer choices A and B, each has a subshell filled to more than its maximum capacity.